Hello everyone. This is a lecture of the kinematics of two-body interaction. In the last lecture, we gave a introduction of the interaction of neutron with matter. We saw neutrons can interact with matter in many ways. One of the most important mechanisms would be the elastic scattering process. So from this lecture and the next couple lectures, we're going to rigorously analyze the neutron elastic scattering process, making use of the quantum mechanics, which we talked about in the early part of the semester, and then describe the energy distribution and also the angular distribution of the scattering process. Okay, so the first step is to examine the kinematics of this two-body interaction. So this part is very general. It's not only limited to neutron scattering process. So in general, we can have a two-particle or two-body interaction. A particle 1 here and reacts with particle 2. Okay. And you can think about this as a scattering process, sending a neutron towards a proton, but can also include other kind of two-body interaction. So after the interaction, then we can get, let's say, two product. One is particle 3. Okay, so particle 3 can be the same as particle 1 or can be different. And then the other product will be particle 4. Okay. So a simple example will be a neutron scattering process. Okay. Let's call the scattering angle to be theta. And the system has a azimuthal symmetry. Okay, so to systematically examine the kinematics of two-body interactions, we need to make use of the Q value. Okay. So, and the final result is the so-called Q equation, so kinematics of two-body interaction. So the final result is the so-called Q equation. Okay, so let's do this. How do we study the system? So first, the total energy of the system is conserved. Okay. The so-called kinematics refers to when we do not know the exact details or we don't worry about the details of the interaction, what can we say in general? So in this case, the energy is conserved, the momentum is conserved. Let's write down each of them and see what these two conservation laws lead us to. So conservation rate of the conservation energy is written as so E1, which is the kinetic energy of particle 1, plus the rest mass energy of particle 1, E1 plus M1c squared. Okay. So that is the total energy of particle 1 plus the total energy of particle 2 will be equal to the total energy of particle 3 plus the total energy of particle 4. Okay, and for momentum conservation is slightly more complicated because momentum is a vector. So momentum conservation will be written as P1 will be the momentum particle 1 plus P2 equal to P3 plus P4. Okay, how many variables do we have? Assuming that assuming we know the mass of all the 4 particles, then we still have E1, E2, E3, E4, and P1, P2, P3, P4. And we know the energy-related momentum, but we still have way too many variables for us. So let's make a few assumptions. The first assumption we're going to make is we assume the first assumption is we assume the target particle 2 is at rest before the interaction. So E2 is equal to 0, or P2 is equal to 0. So this in reality, this assumption applies when the incident energy of particle 1 is much larger than the kinetic energy of particle 2. So when E1 is much larger than E2, then we can assume E2 is essentially 0. And what is E2? E2 is kinetic energy of particle 2. If we think about particle 2, it's in a thermal equilibrium inside certain materials. Let's say a water molecule inside like a tank of water, and tank of water is kept at certain temperature. Then the distribution of the kinetic energy follows the Boltzmann distribution. So then this E2, in general, this E2 would be in the order of kBT. So kB is the Boltzmann constant, T is the temperature. So in other words, if the energy of the incident neutron is much larger than the kBT of the target, then we can assume E2 is 0. Then it means that the target is essentially at rest compared to the incident particle. Okay. Of course, this applies to an important example would be a neutron slowing down process. So after nuclear reaction, we have a fission process. We have neutrons with energy of MeV. Then we can slow them down to sustain the chain reaction. And the slowing down process will be done through this elastic scattering process, sending neutrons through like water at room temperature. Then the neutrons through multiple elastic scattering process is going to slow down to the room temperature. Okay, but initially E1 is much larger than kBT. Then we can assume these waters are essentially at rest. Okay, so if we make this assumption, then coming back to this energy and momentum conservations, then we can get rid of E2 and we can get rid of P2. Okay. Then we can combine these two equations and then see what we can get. So here, P1, P3, P4 are still vectors. It's not that easy to deal with vectors. And we have to separate them into 2 dimensions, one along the x, or in this case, a z direction, the other is perpendicular to z. So the goal for us to simplify these 2 equations will be find out some relations between E1, E3, and E4. Okay, and assuming we know E1, then the question would be, what is E3? Combining the 2, we can get rid of one of them. We can get rid of E4. So E4, let's say, is the recoil of the target particle 2. So what we're interested in, if we use a scattering as example, the question we're interested in would be, given the energy of the incoming neutron, particle 1, then what is the energy of the scattered neutron, particle 3, as a function of theta? Okay. In this case, we can combine these 2 equations and get rid of P4 and E. So how do we do that? From momentum conservation, we have P1 minus P3 equal to P4. Okay. And we know P4 squared would be equal to E4. Then we can combine the 2, get rid of that. So we need to square this. So take the absolute value, and square. Okay. And P4 squared will give us E4. And the first term, P1 minus P3 square, so that be equal to, so P1 square plus P3 square, and minus P1, P3, and cosine of the angle of P1, P3, and that is exactly that angle theta. Okay, so this would be equal to P4 square. Okay, so now what to do next? And we make use of the Q value. So what is Q? To Q value, we'll need to get rid of M4. So Q value is equal to the mass lost. So M1 plus M2 minus M3 minus M4 C squared, or is equal to the kinetic energy gain, should be E3 plus E4 minus E1. Okay, so now we have a P4 square. We can get E4. So this will be equal to E3 plus E4. So E4 would be P4 square over 2 M4, and then minus E1. So now we can substitute P4. This equation becomes E3. Let's move E1 a little bit further. So E3 minus E1 plus 1 over 2 M4 times P4 square, which is P1 square plus P3 square minus twice P1, P3 cosine theta. Okay, so we can further write down P1, P3 in terms of E1, E3. So E3 minus E1 plus 1 over 2M4 P1 square. So P1 over 2M will be equal to E. So P1 square will be 2M1 E1. So P3 square will be 2M3 E3. And minus twice P1 will be 2 square root of 2M1 E1. And 2M3 E3 cosine theta. Okay, so what do we have here? So we have a Q value. Q can be determined by the mass difference of this reaction or scattering. If you know the mass of these 4 particles, then we know the Q value. So knowing the Q value, the left-hand side of the equation is known, and right-hand side of the equation depends on the mass. Okay, the mass is known, and E1 is energy of incident particle, and E3 is the energy of the scattered particle. Then we can solve this equation, solve E3 as a function of E1. And the solution will depend on theta. And that is what we want. So given the energy of incident neutron to be E1, then if you set up a detector at a certain angle theta, then if you can detect the neutron there, then what is the energy of that neutron? Right? So, so this is an equation of E3 and E1. To make it, we can make it look a little bit more clear by collecting the terms of E3. So collecting terms of E3, so that be the first term E3, and this term E3. So that be E3, and coefficient will be 1 plus M3 over M4. Okay, and same thing for E1, that would be minus E1, 1 minus M1 over M4. And the cross term will be 2 over M4 square root of M1, M3 E1, E3 cosine theta. Okay, so Q is equal to this. And this is the so-called Q equation. Okay, and for this Q equation, what you should really consider is given E1. So if we know the energy of the incoming neutron, and we know the mass, and of course we know the Q value of the reaction. Then the question is how does E3, so the energy of the scattered neutron, as a function of theta? Okay, so the variable is E3. If you look at the above equation, so this equation indeed is a quadratic equation. Quadratic equation of square root of E3. The first term will be the square root of E3 squared. And the second term is just a constant. There's no E3. And third term has was proportional square root of E3. So all the rest are just factors, prefactors. Okay. So this Q equation is a quadratic equation of square root of 3. Then we can solve this square root of 3 and solve this E3 essentially as a function of theta. And of course, it's also a function of E1, the mass, and Q value. So this will be the general Q equation. So that describes not only the scattering process, and all these 4 particles, 1, 2, 3, 4, can be anything. It can even describe a fission process. You send a neutron to a nucleus that can undergo fission. Then the product will be particle 3 and particle 4. They still follow this kinematics of this two-body interaction. In the case of a scattering and elastic scattering, now let us look at the elastic scattering. For elastic scattering, what do we mean by elastic scattering? Is saying there's no reaction, so Q is equal to 0. Let's make things even simpler. And the mass, so M1 is the same as M3. It's just the mass of a neutron. Okay? Let's call that small m. And for particle 2 and 3, particle 2 and 4, M2 and M4, they're also the same particle. This is the elastic scattering process. Let's call this target nucleus to be A times m. So A is the atomic, is the mass number. Okay, and m is the mass of neutron. So M2 and M4 will be AM. So then the above Q equation becomes much simpler. So let's write it down here. What do we have? So left hand is equal to 0. Let's keep it that way. And then the first term will be E3 times 1 plus M3 over M4. So that's M over AM, just 1 over A. Okay, so A here, what is A? A is the mass number of the target. Target nucleus. Okay, and then minus E1, 1 minus M1 over M4, that's also 1 over A. Okay, So the Q equation should be, let me see, it's a minus sign. Okay. So we have then minus 2 over a. So M1 is the same as M3, so that become M squared. Take M squared out of the square root, become M. M over AM, that's A. And then square root of E1, square root of E3, cosine theta equal to 0. Okay. So now we can solve E3. You can rearrange this equation a little bit so that we can see this is a equation of E3. So E3, then if we divide 1 plus A over 1 over A, we get minus. So let's move this cosine theta term here first. So that's the square root of E3, and all the rest is just a prefactor. Okay, so prefactor would be 2 over A plus 1, then square root of E1, and then cosine theta. Okay. So prefactor is simply this. So the A cancels out, we have only A plus 1. And then the middle term becomes minus, well, A minus 1 over A plus 1 times E1 equal to 0. Okay. And the first term is E3. You can see that it's the square root of E3 squared. Okay. So it is a quadratic equation of square root of E3. Okay. Then we can solve what is the square root of E3. So square root of 3 will be, so 1/2. So this, the coefficient of second term, so 2 over A plus 1, square root of E1 cosine theta, okay, plus or minus, so, okay, square root of B squared minus 4AC, right? So B squared will be 2, so negative A plus 1, square root of E1 cosine theta squared minus 4, A is 1, C will be A minus 1, A plus 1. Okay, so that's it. Okay, now we can simplify this a little bit to the second term. Okay, if you take the second term, we'll have 2A plus 1 square root of E1 cosine theta plus or minus. Here we have a factor of 4, so factor out. We get a factor of 2, and we get a factor of A plus 1. And then the remaining inside the square root, we have, oh, I forgot about E1 here. So we get E1. Okay, so cosine square plus 1. Okay, so cosine square theta, and then plus, so A minus 1 times, we factor out A plus 1, so it's times A plus 1 and E1. Okay, so the 2 cancels out, this 2 cancels out, and we'll get square root of E1 out, so square root of E1 over A plus 1, and the first term is cosine theta plus or minus. The second term, so that's A squared minus 1, the minus 1 combined with cosine squared theta becomes sine theta. So this will be square root of A squared minus sine theta squared. Okay, it's simple algebra. You can do it step by step. So with A is the mass number, so A is at least 1. If the target is a proton, then A is 1. If the target is heavier than proton, then A is more than 1. If A is more than 1, so the second term inside the square root will be more than cosine square. You take square root of that, then we only need to keep the positive term. Oops. Okay. So we only keep the positive term. Otherwise, we cannot get the square root of E3. Okay. So the square root of so only keep the positive term. Only keep the plus. So otherwise, square root of E3 is a negative number. Okay. So then, what is square root of E3? Would be square root of E1, A plus 1 cosine theta plus A squared minus sine squared theta. Okay. So this will be the solution. How does the energy of the scattered neutron depends on the energy of the incident neutron and also scattering angle? Okay. So again, if you send a neutron towards a target nucleus with the mass number A, then you set up detector at the angle theta, then you can check what is the energy of the scattered neutron, and it follows this simple equation. If you take a look at the two extreme case, if theta is equal to 0, so meaning that you set up detector in the direct beam direction, in the forward direction. Then if theta is equal to 0, then let's see what do we have. So sine square would be 0, then square root becomes square root A squared would be A, cosine 0 is 1, so A plus 1, that cancels out with the A plus 1. Okay, so then E3, it was E1. So that means in the forward direction, this is in the forward direction. In the forward direction, then the scattered neutron has exactly the same energy of the incident neutron. Okay. Then what if theta equal to pi? If theta is equal to pi, then theta equal to pi, then what happens? So theta equal to pi, so E3, we have let's do this calculation real quick. The square root of E3, square root of E1, A plus 1, so cosine theta be cosine pi. What is cosine pi? Cosine pi, cosine 0 is 1, so cosine pi is negative 1. Right? So plus, then square root of A squared or sine pi is still 0. So that is A, so A minus 1. So this is just the A minus 1 over A plus 1 times square root of E1. Okay, so in other words, E3 is equal to A minus 1, A plus 1 squared E1. Okay, and this factor A minus 1 over A plus 1 is squared is used so often. Let's give it a name. Let's call it alpha, alpha E. So alpha is equal to A minus 1, A plus 1 squared. Okay, so this is the backward direction. So when sending neutron, the neutron gets scattered by the target. In some cases, this neutron will be completely bounced back. And then in this case, the energy of scattered neutron is alpha times E. This alpha depends on the mass of the target. This is completely classical. Okay. So the reason that we consider this elastic scattering process it's because of you see it's very simple. We can make this approximation so q is equal to 0, and the final result is simple. Unfortunately, the elastic scattering is also the primary mechanism by which neutrons lose energy in a reactor. So after the nuclear reaction of the fission process, we have neutrons with very high energy, capital M, MeV. Then they are going to get scattered by the moderator, and we can slow down the neutrons. And this moderation process indeed is dominated by this elastic scattering process. Okay, so now we have the energy of E3, the scattered neutron as a function of E1, and the scattering angle. Let me draw a box here. So this is the important result. Okay. Then what do we do next? This is still a little bit complicated for us to understand the slowing down process, the neutron slowing down process, because this only describes one scattering process, and that is the energy of the neutron detected as angle theta. So we don't really care about one particular angle. What really matters is the entire distribution, this distribution of E3. So going back a little bit in the previous neutron-proton scattering process, when we analyze the neutron scattering, we use quantum mechanics, and we learned that the scattered neutron is described by this plane wave. So in other words, if you look at one particular angle theta, the scattered wave function plane wave really has no preference. No matter which angle you see it, and the distribution is uniform. The scattered neutron is described by is a spherical wave function. Okay, so that means like theta has uniform distribution. If we know theta has a uniform distribution, then we can find out the distribution of the scattered neutron E3, and that is what we really care about. Like, what is the distribution of the scattered neutron? And because this process is intrinsically quantum mechanical, so when you're sending a neutron towards a target, and the neutron can be detected in any direction. Overall, it is described by the wave function. But if you only see it at one angle, then there's a finite probability you can detect the neutron in that direction. And the probability is determined by this spherical wave function. Okay, so if you know the distribution, bottom line, if you know the distribution of theta, which is described by the wave function, and we already know, with ice wave approximation, it's very simple, just one spherical wave, then we can find out the distribution of the scattered neutron. Okay, it seems very straightforward, but there's one caveat. So the caveat is when we use quantum mechanics to describe the scattering process, we fix the target. So we fix the target proton. We send the neutron towards the target. Then we analyze the scattering. Equivalently, we can also say that is the scattering is described in the center of mass coordinate. So in the center of mass coordinate, the scattered, the wave function of the scattered neutron is a spherical wave. But now in doing this kinematic analysis, we use the lab coordinate. Going back here, so we use the lab coordination system. Lab coordination system. Sometimes we call it LCS or just L. It's a lab coordination system. So in the lab coordination system, the scattered neutron is not described by a simple wave function of the spherical wave. Only in the center of mass coordinate, the scattered neutron is described as circle wave. Then the distribution is uniform. But in the lab coordinate system, the distribution is not uniform. So we need to do this coordination conversion. Then we can look at the energy distribution and also angular distribution. Okay, so we can do this two ways. So either convert our kinematic equations in the center of mass coordinate, or we can also convert the wave functions to the lab frame. It turns out it's easier to consider the elastic scattering in the center of mass coordinate systems. Let's call this is the center of mass coordinate system. Let's call it CM. So lab coordinate system, we call it L. Okay. So how do we do the conversion? So in the lab's coordination system, we have particle 1 with the velocity v1. Okay. And the target, let's call this as a target, is at rest. Okay. And in the center of mass coordinate system, then what we see is the particle 1 travels towards the center of mass. Let's call it, this is center of mass. Put a cross here. So with the speed v1 prime. Okay, and then its particle 2 in the center of mass coordinate will be seen as moving towards the center of mass. It's v2 prime. So that's before the collision. So after the collision, in the lab coordinate, we see particle 1 gets scattered and leaving with the speed of v3 in angle theta, and particle 4 has a recoil speed of v4. Okay. And in the center of mass coordinate, things are much easier. So in the center of mass coordinate, if you can still remember, in your maybe first year College of Physics, classical mechanics, in the center of mass coordinate, the total momentum is conserved. So so the scattered particles are actually going towards exactly the opposite direction. Okay, let's call this scatter angle to be theta c. So the speed will be v3 prime, and this speed will be v4 prime, and v3 prime is exactly the same as v1 prime, and v4 prime is the same as v2 prime. Okay, so what we know is that the distribution of theta c in the center of mass coordinate is uniform. And now we want to find out the relation between theta and c and theta. Okay, then if we know the distribution of theta c, then we know the distribution of theta. Then if we know the distribution of theta, we can plug back to this equation in the box and find out the distribution of E3. So this is our approach. So now how do we find out the relation between theta and theta c? So, well, this is actually not too hard. In fact, if you combine these two figures together, we can already see the difference. So in the, draw here, in the center of mass coordinate, and this v3 prime is exactly the opposite of the v4 prime. Okay, if you want to convert this back to the lab coordinate, then we just need to add v naught. So what is v naught? So v naught is the central mass speed in the lab coordinate system. So add v naught. So add v naught. then we get V3. So this would be your V3. And same thing for V4. For V4, we add V0. This is V0. We get V4. Okay? Just by combining these two figures together. And this angle is theta, and this angle is theta c in the center mass coordinate. Okay, then we can find out what is the relation between theta and theta c. So cosine theta. What is cosine theta? So cosine theta will be, if you draw a dashed line, will be this distance over V3. So this, what is that distance? So that will be something over V3. So that be V0 plus V3 prime times cosine theta c. Okay. It's a simple geometric relation. So now we can put in what is each of them, V0, V3, and V3 prime. So in the left coordinate, let's write down each of these V0, V1. So what is V0? So in the left coordination system, so V0 is the center of mass speed. So that is the momentum weighted by, so speed average weighted by the mass. M1 V1 plus M2 V2, so V2 is 0, so plus 0, and divided by M1 plus M2. So this is V0, the center of mass speed in the left frame. Okay. And M1 is just M, the mass of neutron. M2 is AM, so this is 1 over A plus 1 V1. Okay. Then we can find out what is V1 prime. So then in the center of mass coordinate, so V1 prime is equal to V1 minus V0. So in the center of mass coordinate system, so the speed of inert particle is slightly less than the speed in the lab coordination system, V1 minus V0. So it's V1 minus V0. V0 is 1 over A1 plus V1. This 1 minus that. So this is equal to A minus A over A plus 1 times V1. Okay. So how about V2? V2 prime, same thing would be 0 minus V0. So the rest, the target particle is at rest in the light frame, but in the center mass frame, it's minus V0. So minus V0 to be 1 is minus negative 1 over A plus 1 times V1. Okay. So and then we have a V3 prime is the same as a V1 prime, and V4 prime the same as V2 prime. You can put it into the cosine theta and find out what is cosine theta. Let me just write down. You can put this back in here and find out what's cosine theta. Equal to 1 plus A times cosine theta c divided by V3, which would be equal to square root of A squared plus 1 times 2A cosine theta c. Okay. So why is that? Just quickly, why is that? So why is this? So because V3, so what is V3? So V3 is equal to, look at this figure drop above, so be V3 prime so have to look at the vectors V3 prime plus V naught. Okay, because in the scattered for scattered velocity, they're not along the z direction anymore. So V3 is this. So same thing. What is V4? So V4 will be equal to V4 prime plus V naught. Okay. Now you can put in the angles and find out what is V3 squared. So that's cosine theta. So V3 will be square root of V3. That's why you see we have the square root of a squared plus a squared plus 1 plus 2a cosine theta c. Okay. These are simple geometries. You can, I believe you can work it out. If you don't, feel free to ask me or a TA. Okay. Then how about E3? So E3, this E3 is one half M3, which is just M3 V3 square. So V3 square here. So M3 is M. Be okay. To take absolute value V3 prime plus V naught square. So that would be equal to 1/2 M V3 prime squared plus V naught squared plus twice V3 V naught cosine theta c. Okay. Let's keep doing this calculation. So this is 1/2 M. So what is V3 prime? Where's V3? V3 prime is the same as V1 prime. So that's just A over A plus 1 V1 squared. Okay. And V naught squared is this 1 over A plus 1 squared V1 squared. And then plus twice. Okay, so twice A over A plus 1 V1 and 1 over A plus 1 V1 cosine theta c. Okay, so if we collect the A plus 1 square term, etc., and this is simply 1/2. Yes. Okay, so we have M 1/2 M V1 square will be E1. So this is 1/2 E1 1 plus alpha plus 1 minus alpha cosine theta c. Okay, so what is alpha? Alpha is A minus 1 A plus 1 square. Okay, so let's write down E3 here and add a box. Okay, so we need this, and we need this. So compared to the above solution, so in above we have E3 as a function of theta. So that is simple, but unfortunately, we don't know the distribution of theta because theta is in the lab coordinate. When we solve the quantum mechanics, we use the center mass coordinate. So our result is we know the distribution of theta c. So we need to write down E3 as a function of theta c. Okay. So now E3 has a very simple form. It's related to the energy and related to the scattering angle theta. And C means it's in the center of mass coordinate. Okay. So now with this, we will be ready to talk about energy distribution, like the distribution of E3. For that, we need a little bit of probability. So, or E1 E1 is a known value, so given the energy of the incident neutron, and want to know the probability distribution of E3. So it is a conditional probability. Knowing E1, then what is probably E3? And the E3 will depend on alpha. Okay, alpha is just a number that depends on the mass of the target. A given target, alpha is just one number. And the theta c has a distribution because the scattering itself is quantum mechanical. So when you send a neutron towards a target, you don't know where the neutron may end up with. It has nothing to do whether you're aiming the target accurately or not. If it's classical physics, then we know, okay, the scattering direction depends on whether you're aiming your target correctly. But in the case of quantum mechanics, we are aiming the neutron towards the target precisely. But the scattered neutron can still go to any of these 4 pi angle because the scattered neutron is described by the wave function. It's a spherical wave function, spherical wave, and has an equal probability to go to all the 4 pi angle. So the distribution of the theta c is a uniform distribution. And integrate that to get 1. So the distribution of theta c is the probability density of the theta c is just 1 over 4 pi. Okay. Not knowing that, then we'll be able to find out the distribution of E3, the angular distribution. The energy distribution, the energy distribution. And from energy distribution, then we can define the energy differential cross section. And knowing the angular distribution, we can knowing the distribution of theta c, we can also convert that back to the lab coordination system and look at the angular distribution in the lab frame. So we know that in the center mass frame, the distribution is uniform, the angular distribution is uniform. We convert that back to the lab frame using the other equation in the box, this cosine theta relation to the theta c. We can find out the essential distribution of theta. Okay, so these are the 2 important informations we want to know. One is the energy distribution of the scattered neutron. The other is angular distribution of scattered neutron. Okay, so that will be the topic of next lecture. Just remember, we're going to come back and to use these 2 set of equations. Okay, that'll be all for this lecture.